Hi, I'm Norman Wildberger. In this video I'd like to talk about a very special number, the number 8/9. We saw that number appearing last time when we were talking about the geometry of a regular tetrahedron. Something like this. Okay. We saw in fact that this 8/9 was the spread between two faces of this regular tetrahedron. Today we're going to see that that same number appears in a quite different context, in the geometry of A4 paper. So let me talk a little bit about paper sizes. There are basically two types of paper sizes in the modern world. There is the 8.5 by 11 letter paper, which is commonly used in the US, in Canada, and in Mexico. That's what I grew up with. The rest of the world uses the A series, in particular the A4 paper, which is exactly this size. So these are actual sizes, and I have a A4 paper here, so there it is right there. Okay, so this belongs to the A series of paper sizes. It was actually introduced, the idea, in 1786 by George Lichtenberg in Germany, and then it was a German sort of push in the 1920s that started growing momentum, and eventually most of the rest of the world fell in line with this, this format. Okay, so we're going to be interested in the geometry of A4. It turns out that this is a very interesting shape. This particular shape has very pleasant mathematical properties. And we'll see in fact that this same number 8/9 appears in the geometry of this A4 paper. So the primary message is about this number 8/9, that it appears in a variety of ways. In fact, it will also turn out to be important when we talk about the octahedron a little while later. But I guess there's another message, which is that generally speaking, our life is full of interesting three-dimensional shapes and configurations, and therefore interesting three-dimensional geometry. And a lot of that interest is partially lost to us with the current obsession with classical trigonometry, with angles, with radian measure, with those circular functions that are used to make the computations, and the heavy reliance on calculators that are necessary to make that kind of thing work. With rational trigonometry, which is what I'm pushing here, we have a completely different way of looking at elementary and not so elementary geometrical configurations. And we get to see the true nature of things much more clearly. So we're going to be seeing direct evidence of that today. In fact, there will be some interesting opportunities for you to make some explorations today. All right, so some interesting practice of actually looking around in our world and seeing all kinds of interesting things that we can actually measure and get interesting numbers for. Now, this A4 paper size that we use for writing letters is only one of a series of paper sizes. So there's not only A4 paper, but there's also A5, A6, A3, A2, A1. So let me explain the relationships here. So this white sheet that I use for my videos is almost an A1. It just has a little bit of an extra border here, but if we chopped off that border there, then that would be exactly an A1 size paper. And it turns out that if we divide that A1 exactly into two, then we get two A2s. So that's an A2 sheet, and that's another A2 sheet. And then if we take the A2 sheet and we divide it exactly in half, then we get two A3s. So that's an A3. And similarly, we take the A3 shape, we divide it exactly in half, say that one there, and we get our A4. And we can carry on from that. So here's an A4, that one there. If I divide that in half, just by folding it, like that, then I get the A5. And if I fold that again, then I get the A6. Of course, I could keep on folding it. A7, A8, A9, goes up to A10 at least. There is also one bigger one. Okay, so if we went in the other direction and tried to get a bigger page size, then we would put two of these A1s together. So if you imagine taking this A1 and then another one, say, on top, then that bigger thing is called A0. It's often used for posters, rather big. All right, so that's the A series of paper sizes, and this particular folding property that you can take any one of the sizes and fold it in half and you get the next lower one is very interesting because the shapes of all of these are exactly the same. They're not different shapes, they're the same shapes, just different sizes of the same shapes. And that in fact characterizes those shapes. All right, so the defining property of the A series of sizes is that by dividing or folding along the long side, this, we get another piece of exactly the same shape. In other words, this folded thing is similar to the original. And that means that corresponding ratios of sides have to be equal. Now that doesn't actually pin down the shapes completely. We also need some normalization to pin down one of them, because there's a sort of an infinite family of possible sizes which all have the same shape. And the normalization occurs with the A0, that big poster size one. So the normalization is that the area of that thing is exactly 1 square meter. So in the metrical system, that kind of works naturally. Okay, so let's analyze the mathematics here. It's very simple. So this defining property specifies this shape. And so to understand what the real shape looks like, let's look at the quadrants of the sides, which we like to do in rational trigonometry. So let's say that this side here has quadrants 1, and this side here, this long side, has quadrants Q. Okay, so now if we're going to fold this thing in half, we're going to get this smaller rectangle of half the size. Then this quadrants from here to here is not half of Q, it's 1/4 of Q. Because Q is a quadratic quantity, and you divide the segment into 2 equal pieces, the quadrants divides by 4. Okay, so the crucial thing is that these two rectangles are similar. So in the big rectangle, the long side to the short side, measured in terms of quadrants, is Q over 1. And that should be equal to the ratio of the corresponding quadrants in the smaller rectangle, which has longer side 1 and shorter side Q over 4. So Q over 1 should equal 1 over Q over 4. Then if we bring that up, we get Q squared over 4 equals 1, and so Q equals 2, because our quadrants are positive. So we get a very simple configuration from this symmetry of the folding giving us the same shape. The conclusion is that the quadrants are in the ratio of 1 to 2. It is a very simple kind of rectangular shape. From a rational trigonometry point of view, it's certainly one of the most natural and simplest shapes that you could choose for a rectangle. Quadrants 1, quadrants 2. Well, you've probably heard about this antiquated theory of trigonometry, which used to be taught with all these classical circular functions, cosines, sines, tans, arctans, pies, radians, and so on. Very cumbersome, old-fashioned 20th century technology, which is on its way out, right? Because rational trigonometry, much more natural, clean, simple, etc., moving in. But anyway, in the classical point of view, taught back in the 20th century, this same rectangle would be looked at in quite a different way. Instead of having nice, clean quadrants of 1 and 2, the analysis went like this. That we're talking about distances or lengths. If this distance is 1 and this distance is d, then the same kind of analysis is that d over 1, this ratio in the big rectangle, should be the same as the ratio of 1 to d over 2 in the smaller rectangle. And then that gives us d squared equals 2. So d equals square root of 2. And of course we immediately have a problem because the square root of 2 is not a real number. It's only something that we write down. It's a symbol, it's a squiggle on a piece of paper, which doesn't actually correspond to a mathematical object, which is completely pinned down. So there's an element of approximation in this classical description of the A sizes. And then when we go on, we want to understand the geometry further. Well, for example, this diagonal, BD. Well, its length will be given by Pythagoras. There's a 1 here, a root 2 here, so that will be root 3. We get another irrationality. And if we want to calculate an angle there, for example, that angle alpha, then the tan of that angle will be 1 over root 2. So the angle alpha would be given by arctan of 1 over root 2, so you have to get out your calculator and ask it for some decimal approximation to something that actually goes on forever. So then it gives you an approximation. So you write that down. You forget about all the rest of the information. And then if you want this angle here, well, these two add up to pi over 2. So this will be pi over 2 minus alpha. So again, you ask your calculator for some decimal approximation to pi over 2, and then you work with these decimal approximations. You get a decimal approximation for beta. And then if you wanted this gamma here, well, you would use this triangle here. This beta plus this gamma should add up to pi. So the gamma should be pi minus 2 beta, which is 1.230959, etc. Okay, so from a classical point of view, it's not very exciting because all these angles are just given by decimals and they're otherwise relatively meaningless. And in fact, we don't actually really know what they exactly are because there's all this trailing information that we've necessarily had to chop off. So it's no surprise that from a classical trigonometry point of view, one looks at the A4 sheet of paper and says, okay, it's 1 root 2, but so what? There's nothing else particularly interesting, perhaps, about it. But it's not right at all. There's actually quite a lot of interesting geometry in it if we look at it in the right way. So let's make a few calculations with rational trigonometry. Quadrants of 1, quadrants of 2. What's that diagonal quadrants? Well, Pythagoras' theorem says that it's 1 plus 2. So the quadrants between B and D will be 3. What about the spread S? This spread right here between the line DC and DB. So one way of thinking about it is that it's the opposite quadrants divided by the hypotenuse quadrants in a right triangle like this. So the S will be quadrants of 1 divided by quadrants of 3. It will be 1/3. And what about R? Well, when you have two spreads like this that combine to give you a right angle or a spread of 1, then it turns out that they actually add up to 1. So this will be 1 minus S, which will be 2/3. And then in this triangle here, if we want to calculate T, this is an isosceles triangle. This is a spread of 2/3. That's a spread of 2/3. So what's the spread T? Well, that's given by this particular expression, 4 times R times 1 minus R. Okay, so that's 4 times 2/3 times 1 minus 2/3, which is 1/3, for a total of 8/9. Isn't that great? So that spread right there, the spread made by the two diagonals of our A4 sheet of paper, is exactly a spread of 8/9. It's exactly the same spread that's occurring in the regular tetrahedron. It's the spread between the two faces of the tetrahedron. Where does this formula come from? Well, this is the equal spreads theorem, which is theorem 51 of my book. And here is the theorem that if you have numbers R, R, and T, and if these form a spread triple, that is, if they satisfy the triple spread formula, then either T equals 0 or T is 4 times R times 1 minus R. Okay, so this is a consequence. Here is the triple spread formula. If three numbers satisfy this thing equals 0, then they are called a spread triple. And if you have three spreads in a triangle, then those three spreads satisfy that S of those three numbers equals 0. That's the rational trigonometry analog of the sum of the angles equals 3.14159, blah, blah, blah. So it's an exercise for you that you can take essentially the triple spread formula and set two of the numbers equal to each other, and then simplify it and see if you can deduce that the third one has to be either 0 or this particular expression 4 times r times 1 minus r. Now it turns out that this particular expression is a very interesting and beautiful expression, that it figures in chaos theory, in fact, in a very important way. What's called a logistic map or logistic function. And here's its graph. If you look at its values from 0 to 1, as r goes from 0 to 1, then it's a nice parabolic arc which bounces around in this 1 by 1 box. And in fact, it's one of a series of polynomials called spread polynomials, which we'll have a lot more to say about in this series at some point. So this is a very important polynomial that will figure prominently, and we've already seen it in some situations already in this series. Okay, so relatively simple analysis. There's been no resort to fancy functions, no resort to calculators, everything just done by hand, a little bit of arithmetic, and we get nice values. Get values that sort of resonate with us, suggesting that the A4 sheet of paper really is mathematically pleasant, and there are probably other mysteries involved in it. Let's have a look at some other questions that we can ask. Great, all right, so here's an interesting exercise for you that starts with an A4 sheet of graph paper and just folds it along this diagonal. So just imagine folding the sheet of paper. There it is originally, and then we're folding it, and this point C down here is reflected essentially in the diagonal to this point. Let's call it C prime up here. So we have this configuration here. And we're interested sort of in the geometry of this configuration. So here's an exercise for you to calculate some quantities associated to this picture. So we folded our rectangle along our diagonal, and now we have various points and spreads and quadrances that we can investigate. So for example, we could ask, what is the spread between this line DC and this line DC prime? Okay, that's a new spread. What is that spread? Now that turns out to be the same as the spread between EA and ED, same as the spread up here. What about the spread between DA and DC prime? The spread right here. In terms of quadrances, what's the quadrants between A and E? Or between D and E, between A and C prime, or between C and C prime. And another spread, the spread between BC and BC prime. And we could do some other things. We could, for example, take the line joining CC prime. There's a new point F there. We could also ask for quadrances, say E to F, or F to G, or F to D, and so on. But I'd just like to ask you one more, the spread between GE and GA. Okay, so that's a nice little challenge for you. So I'm going to take this line right here that we just constructed like this, and another one there like this. And we're interested, what is the spread here? Since all these points are rational, these are all going to be rational numbers. Okay, so they're going to be numbers with some number theoretical content. They're fractions, and it's pleasant to find out what they are. So it's a kind of a little bit of an exercise that will give you this orientation towards looking around in the regular world and seeing some geometrical configuration and asking a metrical question. Right? We can do this. We can ask, what is that quadrant? What is that spread? And they don't have to be meaningless or essentially meaningless answers given by decimals that go on that we have to truncate and then we know no more. No, if we think about things rationally, then we can hope to get rational numbers with number theoretical content. So even in the world around us, sheet of paper, there's interesting mathematics that's waiting to be explored and revealed. So in my Math Foundation series, I've talked a little bit about the differences between dimensions, and that if we're studying two-dimensional geometry in the usual plane and studying two-dimensional geometry in some plane in three-dimensional space, that counter to our usual intuition, the geometry of these things can actually be subtly different. In particular, it turns out that an A4 sheet of paper is not realizable in the ordinary two-dimensional XY plane, in the rational XY plane. But it is in three-dimensional rational space. And when we understand that, we get to see why it is that the 8/9 that appears in the tetrahedron and the 8/9 that appears in the A4 sheet of paper are really the same 8/9. You can make that connection. All right, so the idea is to look at the cube that we looked at last time, the unit cube with vertices, the origin, and then 1 in each of the x, y, z directions. There it is right there. And we're going to look at a particular plane in the cube. Okay, so here's our cube. Maybe here's the origin. Okay, maybe something like this. There's the origin. And what we're going to look at is a particular plane. And the plane is going to be the plane that joins that line and that line. Okay, so imagine a plane that cuts through the cube, through there, cutting down, meeting this. Right? So I'm playing through those 4 points. It's pictured there. It's a little bit at an angle, so you don't see too much of it, but it goes through this point and this point. That's one side. And then this side here up on top. So it has these 4 vertices there. Okay, so this is a rectangle exactly of the A shape, because this side has quadrants 1, as does this side here. The other 2 sides will have quadrants 2, because they are just the diagonals of these faces of the cube. And if that's a quadrant 1 and that's a quadrant 1, then that's got to be a quadrant of 2. And so, similarly, that's a quadrant of 2. So that's a nice little rectangle exactly of an A shape sitting inside our cube. So slanted inside our cube. And if we look at the 2 diagonals of that rectangle, then those are diagonals of the cube. And we've just established that since this is an A sheet of paper, then those diagonals have a spread of 8/9. That's telling us that in the cube, if we're at the center of the cube, which is the same as the center of that diagonal plane, and we're looking up at 2 vertices which are at endpoints of an edge, then we're seeing a spread of 8/9. Or to put it another way, if we're just looking at the 2 diagonals in the cube from the center of the cube, then those 2 diagonals will make a spread of 8/9. So this connects the 8/9 that coming from the tetrahedron story and the 8/9 coming from the A4 sheet of paper. So I hope you've enjoyed that small excursion into the Platonic solids. We're going to have a look at Platonic solids more generally now. So the tetrahedron and the cube are just 2 out of 5. There's also the octahedron, which is very close to this story in a number of ways. And then there are these other 2 mysterious ones, the icosahedron and the dodecahedron. Very long and illustrious history, very important and interesting mathematical objects. And with our orientation, we're going to have new things to say about these very classical objects. And also kind of opens the door for actually some big investigations in hyperbolic geometry. So looking for analogs of the Platonic solids in hyperbolic setting is a very, very interesting story. All right. So next time we'll have an introduction to the Platonic solids. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.